Welcome everyone, I'm Konstantina, and in this section we're going to speak about linear regression. So what is regression? Let's say we have a set of continuous values and we want to predict some future or missing value. In regression we have continuous valued functions, so it's not like classes. They could range from 0 to 100, and the idea is to use the available data, like for example these two green lines, to predict what might happen in the future, or to predict some missing value in between. And what comes first to your minds is that the line will pass the question marks, but do we really know? And the answer is no. In linear regression, the assumption is that we have a constant linear dependence between the observation value we're interested in and another variable. And how do we find out if we have a linear dependence? So here, y is the dependent variable and x is the regressor, or the independent variable. And our observation should follow a line described by a y-axis shift beta 0, a slope of our function beta 1, plus some epsilon. And we want to find the beta 0 and beta 1 that describe this function. So how do we calculate beta 0 and beta 1? And the answer is with the least squares method. So we have our given points, and as an initial prediction, we draw a line connecting two points. Then we measure the distance of all the other points from the line, and we realize that is far from the best value. So we adjust the values of beta 0 and beta 1. So in the overall process is that we always estimate how far away the points are from the line, and then we correct the line to improve in every step. This principle is called expectation maximization. We make a prediction and then we update the model parameters, in this case beta 0 and beta 1, in order to fit the line in the best possible way. So far, we assumed that the data has a linear shape. However, there are several more advanced cases of regression, like the locally weighted linear regression, that is suitable for data that is not purely linear, but follow a more wavy-like line, as in the upper left graph. In this case, if we used linear regression, the result would be like the upper right graph. This line may predict what will happen in the future, but it does not take into account the local variations of the wavy data. And if we use the locally weighted linear regression instead of a whole model, local models are created in neighbors. So having a query point, the model will take into account more the closer data points and will assign a higher weight than the far away points. And in this case, a very small k, like 0.003, we end up with a line that connects all the points to one another. But this is too noisy and cannot predict the behavior of the data. Another method that could be used for piecewise constant data is the tree-based regression. For example, you may have data from an elevator that goes in specific floors and rarely in between. In this case, instead of trying to fit some linear model to your data, you can use this decision tree-based approach, where you build a tree for constant data. This method can fit complex, nonlinear data, however, it may be difficult to interpret. Another interesting case comes when data are piecewise linear. So we may have one slope for some interval, and then some event may occur, and then the slope changes. In this case, we find where there is a good point to split the data, and then we fit linearly in each interval. And as in linear regression, we use expectation maximization to fix the splits and slopes. And here is a comparison of tree-based methods on some artificial data. So if you apply just the default linear regression, you will end up with a model on the left that has a high error in the points that are very far from the predicted line. If we would apply a linear tree, then we would end up with the model on the right. And we see that it fits much better than the default, and instead of a linear tree, a polynomial tree would fit even better, especially in the curves of the data distribution. We should keep in mind, though, that it is not easy to predict what might happen. And in this case, we have a Google search trend on snowboard, And we see that as years pass by, snowboard trend is decreasing. So we would assume that after 2016, it will keep increasing. But the truth is that it stays constant, as we see in the faded red line. So we cannot really predict what is going to happen, and one way to deal with these complex situations could be neural networks. Thank you for listening.